Thank you very much. So we as a community, we're interested in entanglement. Some of us even gathered here in Taipei in a wonderful conference just to talk about it for a few days. And here in this talk, combining 3 different papers, we're going to investigate in these wonderful list of collaborators some very basic properties of some tripartite asymptotic measures that, interestingly, we didn't and still, for some of them, don't know yet. Okay, so the asymptotic regime where we take many copies or many rounds, it has been very prolific in quantum information in many areas, in channel capacities, in on-local games, in communication complexity, quantum query complexity, and in the subfield that I'm going to talk about today, multipartite entanglement measures. When we talk about entanglement here, we're talking in the operational view. So we're talking in the lock framework. And when we talk about bipartite states, we know quite a lot about them. But just introducing one more particle and talking about tripartite state, suddenly there's a lot of ways to quantify entanglement, and we understand very little these ways themselves. And this is what I'm talking about today. This does not quite work. Okay, so the results in high level are that we show for some asymptotic entanglement measures that the set of values they take are discrete in some regimes. These include very used ones, so asymptotic rank, asymptotic slice rank, and asymptotic subrank. And we also show, or rather 2 papers I'm not on, show specific first few values of asymptotic slice rank and asymptotic subrank. So the talk will continue with the definition so that we can understand all of the stuff that I just said better. We understand it better, and then we go into a little bit of the ingredients, specifically 3 ingredients we think are interesting all by themselves. Okay, so as I started to say, we are talking in the lock framework, LOCC. So we take the particles, we put them in different labs, we allow the labs to operate with local operations and classical communications, so operating on their own particle and talking with any classical means, for example, the telephone. And this is the lock framework of thinking of an entanglement, of defining it in a way. And this has been very successful in understanding entanglement. We understand bipartite states quite well. We know majorization theorem by Nielsen, and if in the relaxed SLOC framework, which I'll introduce in a bit, we understand everything because a bipartite state is basically just a matrix, and we can think of the rank, which is the Schmidt rank, by Gauss elimination. So everything is nice and clean. But when we introduce the 3rd particle and give it to Charlie, suddenly it becomes much more complex. And asking them to convert a state to another state in the lock framework, we can only kind of hit some barriers and cannot really say a lot currently. So if we relax this into the SLOC, so SLOCC, adding the stochastic, meaning that we allow the conversion from one state to another to occur with any positive probability, no matter how small, then the conversion, the conversion and the operations that they are allowed to perform can be made very simply, neatly, clearly in mathematical form. And this mathematical form is just, if we remember that the tripartite state is just a cube of numbers, we can think of it as a 3 tensor, cube of numbers, then the SLOC operations are just 3 local linear transformation. That's all. What do I mean by that? So for example, Bob can use any linear combination of the slices in his direction. What's his direction? The yellow slices. Now, the fact that it's nice and clean doesn't mean anything if it can't give us anything, but it does give us anything. And that's why we talk about it, and we talk here about asymptotic Slock monotones. So let us define what they are. They are functions that are monotone under local linear transformations, and they respect tensor exponentiation. Okay, and if we remember that Slock is a relaxation of lock, any barrier for Slock conversion is also a barrier for lock conversion. So giving two tripartite states and a asymptotic Slock monotone for which we can show a strict inequality in the other direction of the monotonicity means we have a lock conversion, which is what we wanted in the first place. So this is the motivation of why look at asymptotic Slock monotones. And now I can start and define the protagonist, the main protagonist of this talk, the subrank and its asymptotic version. So we start with a psi, with a pure tripartite state, and we ask Alice, Bob, and Charlie to Slock convert this state to one of a very specific kind of states called GHZ states. And here I'm talking about GHZ with many levels, not just two. And the question is exactly how many levels they can create by Slock actions. And the maximum amount of levels they can create in a GHZ is the subrank denoted Q. So if we remember that a tripartite state is just a cube of numbers, these look just like a diagonal, and the size of the maximal diagonal they can create, Slock create, from the state we're talking about is the subrank. And what's its asymptotic version? It's as we normally regularize or normalize in the asymptotics. We take many copies, we ask them to create many copies, the kind of the same amount of copies of GHZs, and then we again look at how many each of the copies has. So mathematically, this is the regularization that's going on. And make note that this is, and we denote this asymptoticity by this tilde below the Q. And this does not need to be, and normally, usually it isn't the same as the subrank, because now, for example, Alice may operate on all of her particles together to create these. Good. Another measure that will appear a lot in this work is the asymptotic slice rank. I'm not going to define it in the same detail amount that I did with the asymptotic subrank, but I will say that in the way that asymptotic subrank is starting with our state and preparing GHZ states, the asymptotic slice rank is the other way around. We start with specific kinds of states. I'm not going to define them. They are kind of bipartite entanglement stuff in a direct sum way, and prepare the state asymptotically, the state that we are interested in. The slice rank was introduced and used by Tao and Sawin for combinatorial problems, and it was used and is still used very successfully for the capset problem. And the asymptotic version of it was shown by Christenel, Vrana, and Zaudem to be characterized by entanglement polytopes. So they have intimate relationship with the tripartite measures. So now we can finally understand what the results is. So what we're aiming at here is understanding the sets that are the values, the images of the parameters that we just talked about, the asymptotic slice rank and the asymptotic subrank. So going over all of the formats, N1, N2, N3, let's call it a format, all of the tripartite states possible, pure tripartite states, what are the different values that these parameters can take? How does it look like in the real line? It might be just the whole real line, it might be some countable but dense subset, and it might be a discrete set or some mixture of all of the above. So when the subrank was introduced and the asymptotic subrank together in 88 by Strassen, he already showed that the asymptotic subrank can only take the values 0, 1, or at least 2 to the 2/3. So it is gapped in the beginning of the line. Then Costa and Leigh improved this bound to 2 to the entropy of 1/3, and 2 of the 3 papers in this work improved it further, and both showed that this 2 to the entropy of 1/3 is the correct number. And by the way, it's all for asymptotic slice rank as well, and showed the 2 next values, which are 2 and something like 2.69. Look at the paper for the exact definition. It doesn't really matter here. So good. So we know that at the beginning of the line, it looks like gapped. What happens at the rest of it? So the characterization of the asymptotic slice rank by entanglement polytopes, and by the fact that there are only finitely many polytopes for any format N1, N2, N3, which is a remarkable fact by itself, means that for asymptotic slice rank, it cannot be continuous, right? There are only countably many formats, N1, N2, N3, and for each one, there's only finitely many entanglement polytopes, so countable. Blatter, Dreisma, and Rupniewski generalized it for any algebraic parameter, and I'm not going to define it, but it's a very general condition. So we know it for asymptotic subrank and for many others as well, that they are not continuous, so they cannot also have some continuous subset. And we show that it's also not dense, so it is discrete. And what we mean by discrete, we don't mean the gaps are the same everywhere. What we do mean is that in this subset, there are no accumulation points, or equivalently, if you take a sequence from this subset that converges, this sequence must become constant at some point. So there are gaps everywhere. And here is again the theorem a bit more precisely. So the set of values of the asymptotic slice rank over all of the tripartite states in all of the formats is discrete. For the asymptotic slice subrank, we have something weaker, which is only for any finite set of coefficients. If you take all of the tripartite states over this set of coefficients, but still over all of the formats, this is discrete. And well, our theorem actually is a bit more general, but see the paper for more details. Good. So now I can go ahead and talk a little bit about the ingredients. So the first 2 that I'm going to talk about are lower bounds for how large how large of a GHZ can we distill from any state. And this lower bound will be in terms of local dimensions. So let's denote them by the blue lines here. They don't need to be the same for the 3 different particles. And of course, a tripartite state doesn't need to use these local dimensions, so it cannot be just like that. So it's only for concise states, which again, I'm not going to define exactly here, but what it means basically is the tripartite state is actually using up all of the local dimensions. And if it does use up all of the local dimensions, we can give a lower bound of the number of support in the GHZ state that we can asymptotically distill, and it's by taking the minimum of the 3 local dimensions, and it's the cubed root of that. Okay. The second version of this lower bound is only for tripartite states which have a very unbalanced local dimensions. So if 2 of them are much larger than the third, then this lower bound can be upgraded to the maximal possible. So get rid of the cube root. And mathematically, here is the statement. So for every local dimension, there is a threshold after which, if the other 2 dimensions surpass, we have the maximal subrank possible. Good. So let me show you how the theorem follows from these 2 ingredients, these 2 lemmas. So we're going to do this second statement first, and I'm going to only mention how the first one is kind of the same. So we start by noting that for a finite set of coefficients and for a fixed format n1, n2, and 3, there are only finitely many tripartite states, right? You have only finitely many coefficients, only specific local dimensions, only finitely many states, and thus only finitely many values of asymptotic subrank of such states. Good. Now take a sequence of states, and we want to say that the sequence of asymptotic subranks of them, if it converges, it must be constant from some point onward. So take a sequence, first convert each of the tensors to a concise tensor that is equivalent. We can always do that. We can always do that without changing the set of coefficients, and we can also do that without changing the asymptotic subrank. The only thing that might change is that they might be not normalized anymore. Good. And now we have 2 cases to consider. Either I have in that sequence, I have local dimensions in all 3 that grow, at least in a subsequence. And if that is the case by the first lemma, I see that the asymptotic subrank, at least in some subsequence, grows as well. So I don't have convergence. Good. If, on the other hand, I have one of the local dimensions bounded, then in order not to stick around with only finitely many values and go through some cycle of them, I'll have to have the other 2 local dimensions grow. And once they grow enough, the second lemma will kick into action and we'll get the maximal possible from that point onward. So we have a constant tail of that sequence. Good. Wonderful. So we have the second statement. What about the first statement? So the first statement is actually the same when you know that the asymptotic slice rank is lower bounded by the asymptotic subrank, which is by tau. And when you know by the characterization that we talked about before that for every format, although we have infinitely many tripartite states, but we have only finitely many entanglement polytopes, so we only have finitely many asymptotic slice ranks. And then it all goes through. Good. So let me tell you about the third, and I think very interesting ingredient, which is tripartite to bipartite entanglement. So let's say Charlie is a saint and he wants to aid Alice and Bob to get as much of bipartite entanglement as they can from the tripartite state. So what we said he can do is he can take, linear combinations of his slices. So he does that, and together with them, they create an EPR unentangled from his particle. And the maximal size of the EPR, again, not just 2, the maximal that's possible, that would be called max rank in his direction C. So Q sub C of the state we started with. And this was already considered, and maybe I don't have a lot of time, so I'm not gonna say exactly the progression. It has been a long time since it has been introduced. But what we add to the conversation is that looking at 2 different directions. Take any 2 directions, let's say Alice and Charlie, then they cannot, they cannot both have too small of a bipartite state they can help the other 2. What I mean, again, so for any 2 directions, the product is lower bounded by the local dimension of the third particle. And again, this is for concise tensors, but every tensor is equivalent to a concise tensor. Yes, and that's it. So I just want to conclude with some open questions, which I think are quite nice. So of course, we have few of the first values of asymptotic subrank and asymptotic slice rank. We know at least that the asymptotic slice rank is gapped, so there must be more and more next values, which are there. It looks a little bit more problematic than these, but maybe it's possible. The lower bound, the first lemma that I showed, we showed a cube root of n. We think the right answer is squared root, both because the best example we know of is Strassen's null algebra, which grows like squared root, and also because we show square root for symmetric tensors. So we believe this is the right answer. We don't know. We also believe that the asymptotic subrank is discrete over all of the complex numbers and not only for finite set of coefficients, but we haven't been able to show it. And it, of course, will be nice to show discreteness over 4 particles, 5, and so on. So I would like to thank you for attending and my wonderful colleagues and collaborators for working with me.
Okay, we have a little bit of time for questions. Anybody?
So I have a not mathematical question, and for that I apologize, which is how should this result, which is surprising and awesome, thanks, change my intuitive understanding of tripartite entanglement?
That's a very nice question. I guess I would start with asking you, what is your intuition for tripartite? Like, I don't think we have a lot of intuition for tripartite, quadpartite, and so forth. Like, I think most of the stuff that we know is looking at stuff as if they are bipartite, but in some sections, so bipartitions. And once you look at the stuff as they are, tripartite and forward, it becomes dependent on what you want to do. That's why we're talking about measures and not measure. Like in the bipartite, it's kind of, you know what to do. If you want a crude one, look at the Schmidt rank. If you want a more interesting one, look at the entropy. We don't have that. It's really like a zoo, like someone said yesterday. So I really don't know, like, with what intuition do you come with? But I think this exactly points to the fact that we can't even know if I don't know if can't, but we don't even know for some measures if the values are gapped, if they're discrete. What does it look like? It's a very simple. It's a very, well, not simple, basic question. So I find it weird that we don't know it.
Maybe we have time for another very quick question.
Oh, hey, sorry. I have a really naive question. So for the rank of the tensor, is a tensor like a joint spectral intensity matrix type of situation, or
Joint what? Sorry.
a joint spectral intensity?
So we're talking only about pure states.
Okay. Oh, okay. Thank you. Yeah.
So pure tripartite states, which you can think of as just a cube of complex numbers if you think of the computational basis in each of the particles. So it's just in the ijk place, put the amplitude of the ket ijk.
All right. Cool.
So-
Thank
so
you.
that-
Anybody else? I mean, I have a small curiosity, so I didn't quite get. So, what are the main hurdles to generalizing this for more than 3 parties?
So the lower bound, for example, we use it very strongly. We don't have it for 4 particles. There are. You could have partition 1 particles which are entangled on 2 pairs already, and that's already like kind of a barrier for stuff that we do in the paper that allows us to do the lower bound. So the techniques as they are don't quite go through. We tried a little bit, we failed a little bit. Yeah.
Okay, thanks a lot. No more questions, I guess. Okay, so let's thank Itai and all the other speakers again.
Thanks.